Welcome to the lecture on adding and subtracting radicals. In order to add or subtract radical expressions, the expressions must contain identical indices and identical radicands. That means the kind of radical that you're taking, for example a square root or a cube root, has to match, and the numbers under the radicals, which is called the radicand, must match as well. So if we look at this first example, 16 square root of 2 minus 18 square root of 2. They both have square roots and they both have 2's underneath the radical. So we're able to subtract. When you subtract radicals, you subtract them just as if they had variables. So think of this as like a 16x minus an 18x. You're only going to subtract the coefficients out front. So 16 minus 18 is negative 2, and the square root of 2 stays put. So our solution, negative 2 root 2. On the next one, we have 6 square root of 18 minus 5 square root of 32. Initially, it looks like the numbers under the radicals don't match, so we can't add these. These would not be considered like terms. However, what you have to recognize is that 18 is not a reduced square root because it's divisible by a perfect square, and so is 32. So before we try to subtract, we need to simplify these two radicals first. So I'm going to leave the 6 on the outside, and then I'm going to break up square root of 18 into 9 times 2. So square root of 9 times square root of 2. The square root of 9 reduces to 3, but that 3 is going to get multiplied by the 6 that was already on the outside. So the whole term becomes 18 square root of 2. On the second example, our second term, we're going to do the same thing. We're going to leave the minus 5 on the outside, and we're going to divide 32 by the largest perfect square factor. 4 works, but 16 works too, and it's bigger. So we're going to write 32 as square root of 16 times square root of 2. Square root of 16 reduces to 4 times the minus 5 that is already out front. So negative 5 times 4 becomes minus 20 root 2. So after we've simplified our radicals, we now do have matching radical terms, square root of 2's. So we're able to subtract the coefficients out front. 18 minus 20 is negative 2, and the square root of 2 just stays put. Okay, and the next example, same thing. We've got 32, 48, and 128. All of those numbers under the radicals are not reduced because they're divisible by perfect squares. So just like in the last problem, the square root of 13 we're going to break up into square root of 16 times square root of 2, and the 4 out front stays put. Square root of 16 turns into a 4, and that 4 times the 4 that was already out front makes this 16 root 2. When we go to the square root of 48, you want to run through your list of perfect squares and try to find the largest perfect square that divides into it. 4 works, but so does 16. So we're going to use square root of 16 times square root of 3. 16 times 3 is 48, and the minus 3 that was already out front is going to stay put. So the square root of 16 turns into a 4 times the minus 3 that was already there. So negative 3 times 4 is negative 12 root 3. And then when we get to the last term, square root of 128, 128 is divisible by 64. 64 is a nice perfect square, and 64 times 2 is 128. And if you don't know these off of the top of your head, then you can just run through your list of perfect squares, and using your calculator, just try dividing those perfect squares into 128 until you find the biggest one that works, that divides in evenly. So I am going to leave my plus 4 on the outside and break up 128 into square root of 64 times square root of 2. Square root of 64 is 8 times the 4 that was already out front. 4 times 8 is 32, so we get 32 root 2. So now all of my radicals are reduced. We're ready to compare them and see if we have any like terms. The square root of 2's here and here match. So only those two terms get to be combined. The minus 12 root 3 doesn't have anything to combine with, so it's just going to stay in the problem unchanged. 16 plus 32 is 48 square root of 2, and that minus 12 root 3 just gets carried down, and here's our final answer. Okay? On the next example, we have some variables involved. So again, we need to have matching indices, which means matching square roots, which we do have, but we also need the numbers underneath to match as well, and that would include numbers and variables. Right now they don't match, so I'm going to look at this square root of 20 y squared and see if I can reduce it. First of all, 20 we know is divisible by 4, which is a perfect square. So let's break up 20 into square root of 4 times square root of 5, and I'm also going to give that y squared its own radical as well. Square root of 4 turns into 2, square root of 5 will stay put, and remember square root of y squared, square and a square root cancel out, so this is just going to give us a y on the outside. Rearranging the terms a little bit here, I'm going to just push together my 2 and my y and put that in front of my square root of 5. So now this first radical is reduced. The second radical can be brought down, it's already reduced. And now we notice that we do have like terms. Not only must the radical parts match, but since we have variables, to have like terms, the variables must match exactly and have the same powers, which they do. They're both y to the first. So these are like terms. All we have to do is subtract these coefficients. 2 minus 3 is negative 1. The y stays put, the square root of 5 stays put, and you don't even really have to write that 1, so we could just write negative y root 5. And there's our solution. Okay, on the next example, we're going to do the same thing. We want 8k times the cube root of 54k plus 6 times the cube root of 16k to the fourth. So let's start with our radical right here, and we want to make sure it's reduced. I'm going to leave the 8k on the outside. Now this time we are talking about a cube root, so we need to think about those perfect cubes. 2 cubed is 8. 8 does not go into 54. 3 cubed is 27. 27 does divide into 54. 27 times 2 is 54. So this radical can be reduced by breaking it up into the cube root of 27 times the cube root of 2, and I'm going to leave that cube root of k under its own radical. Cube root of 27 turns into a 3 times the 8k that was already outside, and the cube root of 2 and the cube root of k will stay underneath. In the case of the k's here, I only have k to the first. I would need to have k to the third or higher in order to be able to reduce anything. So these are already simplified. So now just to clean this up a little bit, 8k times 3 is 24k, and let's just push these two into the same radical, so we get cube root of 2k. So there's our first term simplified. Now we're going to do the same thing on the second term. So we have cube root of 16k to the fourth, which we're going to try to reduce. The 6 on the outside is just going to stay put. And then think about those perfect cubes again. 2 cubed is 8. We know that 8 divides evenly into 16. So if I break up 16 into the cube root of 8 times the cube root of 2, and also write that cube root of k to the fourth on the outside as well, under its own radical as well. We're going to try to reduce as much of this as we can. Cube root of 8 turns into 2 times the 6 that was already out front times the cube root of 2 that I can't reduce. And here this time I have 4 k's. I only need 3 to be able to pull one out. So this should reduce. How do we reduce it? Remember, you divide. 3 goes into 4 once, so we're going to get 1k on the outside. But when we divide 3 into 4, we also have a remainder of 1, so there's 1k on the inside as well. Now let's just clean this up. We have a 6 times a 2 times a k on the outside. so that's 12k. And if I push these two radicals together, we get cube root of 2k. And this was a positive term because we had a plus sign in between. So now we've simplified our radicals. We're ready to see if we have any like terms. Not only must the radicals match exactly, but any variables on the outside must match exactly, and in this problem they do. So we're ready to combine our coefficients. 24 plus 12 is 36. The k stays put, and the cube root of 2k stays put. So our answer is 36k cube root of 2k. Don't forget to write that little cube root index in there. Okay, on our last example, we're going to do the same thing. If you look at this first term, we know that it's not reduced because I have 5 m's under my radical. I only need 4 to be able to pull some out. So this is not considered reduced. So if I divide 4 into 5, it will go in once, so 1 m will come on the outside. But when I divide 4 into 5, there's a remainder of 1, so there's going to be 1 m left underneath the radical as well. And don't forget that we had that 5 out front. So the first term becomes 5m fourth root of m. For the second radical, we have this 3 on the outside, and now we're going to try to reduce our radical part. If you think about perfect fourths, 2 to the fourth is 16, 3 to the fourth is 81. So the fourth root of 81 is a perfect fourth already. It's going to reduce to 3 times the 3 that was already out front. In addition to the 81 reducing, we also have that fourth root of m to the fifth. That's going to reduce as well because 4 goes into 5 once, so we'll have 1 m outside, and 4 divides into 5, leaving us with a remainder of 1, so we'll have 1 m left underneath as well. So we get 3 times m, or 9m, fourth root of m. And that's how the second term combines. So when we add that to our first term, the m's on the outside match, the radicals match, so 5 plus 9 is 14m, fourth root of m. And there's our solution. Okay, that concludes our lecture on adding and subtracting radicals. Good luck.